All right, welcome to Math 150, Section 2, Lecture 22, 23, something like that. So the purpose of the domino exercise was to give you an opportunity to try to think outside the box. I was deliberately vague as to exactly what are the instructions. So actually, Kim, can you give me just a few of the bigger dominoes? Because those are better for the camera. Say 4. So we're going to define an overhang as the distance from the bottom domino.
What was the best overhang?
It's really tough to say what the best overhang is.
No, like what was the farthest?
The farthest was, I think, yours of about 3.5, and it depends on how many dominoes you're using. So one domino is about 2 units in this Williams-approved tape measuring system. Okay, so there's a lot of creative things that I saw people doing. Some people were having dominoes at angles. Some were having dominoes perpendicular to each other. And the more freedom you have, the better you can do, or at least the better chance you have of doing better. You can't do worse if you give yourself more options. But also the harder the analysis becomes. So some people discovered that it's actually good to build in both directions and use that to help you out. Sometimes you take 1 step backwards, take 2 steps forward. So what I'm going to do is I'm going to talk about the analysis under the restriction that we can only build in one direction. That's much easier than the more general case. And so if I have one domino and I put another one on top, what's the best I can do for my overhang? Half a domino. If I have more and more dominoes, then it becomes more interesting. So if I have 4 dominoes and I allow myself to build in both directions, one of the possibilities, which a lot of people have tried to do, is something like this, where you have a big hole in the middle and then you're building in both directions. And then if I continue this pattern, I could put another one here, one's on top, and put some mass on the bottom to hold it down. And so the more dominoes I have, the further I can go. I will do the analysis just in moving in one direction. Okay? Now the first thing you have to decide is what you want your unit of measurement to be for a domino. How long is a domino? A domino long. That's the unit. There are a lot of great units in the world. There is the Bruno from MIT. It's the indentation in cubic centimeters from dropping a piano off the 2nd or 3rd floor of a building. There's the Snoot, which you'll find out about on Monday. There's the Milli Helen from Isaac Asimov. There's a lot of very interesting units of measurement. Now the question is, do you want to have a domino 1 domino long or 2 dominoes long? Yes, 2. Why 2? Yeah, they're cut in half. And so that's why I really like these ones. I have no idea how good the resolution will be on the camera. But if you see a lot of them, they have a line halfway through. Actually, the 6 is a good one with the 6 and the 0. And so if I put my first one over, I'm going to get an overhang of 1 unit. So again, it's not necessarily clear to begin with how you want to normalize things. Where do you want to have the center of your coordinate system? Do you want to have it at the end of the domino or the middle of the domino? Where do you think you'd want to have the center? The middle. So we're going to do the center is going to be in the middle. All dominoes will be 2 units long. And we will first do the analysis of 2 dominoes. So we're going to need a very small amount of physics today. So we need to make sure that the center of mass is always protected. Okay? So if this domino is pushed too far, it's going to fall. The center of mass has to be resting on the first domino. So the furthest we could push it is exactly halfway along. Okay? You might argue as to whether or not this is stable. We will assume it's perfectly stable. There's no big construction trucks today driving down. When I was in high school, I took a physics class at Harvard, and the professor took a 450-pound pendulum, walked up to the blackboard, moved it like this, and stopped just before his nose and said, "I have complete and utter faith in the laws of physics," and then released it. Now, if enough of us had stomped our feet and whatnot and shaked it so that the ceiling started to vibrate, we would see how much he trusts the lower order terms in physics. But if everything is perfectly, no friction, no wind, no shaking, no vibrations, it will not go further than how he releases it. So we will assume that the domino can be held perfectly like this. So what is the overhang with 2 dominoes? It's how much? The overhang is not 1.5. What's the overhang?
1.
The overhang is 1. So the furthest point from the bottom domino is 1 unit. Okay? This is how we're going to define overhang. And in the simple case we're using, each domino must be above exactly one of the dominoes. We're just marching down to the left. This is a very simple case. The more general case, where you allow yourself to go backwards and forwards, has an incredibly different answer. And in fact, one of the people who proved it was my math professor, my very first math professor at Yale, Yuval Perez. So here the overhang is 1. The next thing I want to calculate is what is the center of mass? So I have one thing here at 0. Its center of mass for the bottom one is at 0. Where's the center of mass for the top one? It's at 1. And so where's the center of mass? At what place? It's in between. So what would it be? It would be 1/2. All right. So now let's look at 3 dominoes. So what I want to do is, here's my ground domino, 0 and 1. I want to take the domino configuration that I know works so well with 2 dominoes, and I want to put it on the bottom one. If I put it directly on top of the bottom one, is it going to hold?
Yes.
Yeah. I mean, really, there's no need to have one here. I want to see how far can I push this. And I can push it up until the point when the center of mass of these 2 is no longer above this. So I want the center of mass of these 2 to be right above the corner.
Which needs a more rigorous definition than that in theory, because you could just stack them all on the side, the center of mass would stay in the center, but
Wait, what do you mean by stack them all up?
well, because you could just keep you keep the center of mass the same if you just keep stacking them all on the sides, but that won't.
Well, can you show me what you mean? I don't.
Like if you just keep one in the center and then stack 2 like that, they'll fall.
You should please show me with dominoes.
Okay.
So I'm not following how you're configuring.
I just mean if you keep.
But now we're
These
moving in,
would
but
stay.
now we're moving in both directions. We can only move in one direction right now.
Okay. Sorry.
So right. So right now we're only moving in one direction. Okay. Okay. Good. Excellent. You might be moving up to 3 desserts. But of course, if Cam's mother's watching this, we would not give him 3 desserts for lunch. That would be wrong. So we're moving in just one direction. Okay. You have to be careful when it's being recorded. Okay. So we want the center of mass to be exactly over here. If the center of mass of this is 1/2, then that means it's half a distance to the center, and then it's another whole unit to the end. So the center of the bottom one is right here, and then I have to go back with another whole unit, so I would be at -1/2. And that's where this brick would start, and this would go all the way to 1.5. Does everybody agree that that's where the second domino would be? And now the third one, this one starts right above the center. And so it goes over 2 units. The center of this one is at 1/2. So this goes all the way up to 2.5. So what is the overhang? Okay. And now what's the center of mass? So there's a couple of ways to do it. So one is to look at the locations of the 3 masses. So for this one, it ends at 2.5, so its center of mass is at 1.5. So we would have 1.5, well, I'll do it maybe 3/2. 3/2 for this one, plus this one is at 1/2, and this one is at 0. They all have a mass of size 1, so they're all weighted equally. And then what do I have to divide by? 3, because I have 3 masses. And that would give me the center of mass. So I would have 3/2 plus 1/2 is 4/2 divided by 3 is 2/3. So I get the center of mass is 2/3. There's another way we could have calculated the center of mass. We know the center of mass of this whole thing is a half a distance, a half a unit from the center of the second. All right, where is the center of the second? It's at 1/2. So the center of mass of this whole unit is at 1, right? So it would be 2 masses at 1 plus 1 mass at 0 divided by 3. And I also get 2/3 that way. So there are 2 different ways to calculate the center of mass. As you have hopefully learned by now in my class, most of the difficulty is not the actual calculus, but the algebra. Are there any other ways of writing the number 1.5? How else could we write 1.5? I'm sorry?
5/2.
Not 5/2.
I don't know math. 3/2.
3/2. So we could also write this as 3/2. How else could we write 1/2? 1.5. Doesn't have to be just fractions. You could, I'm sorry? 1.5. You could do it as 1.5. But there's another way that's an addition problem. No, if you've been in section 1, you're not eligible. How can I write 1.5 as an addition problem?
1 plus half.
1 plus a half. And so the question is, which is the best way to write the answer? Let's start keeping a tab of what we've seen. So we'll have our conjectures. So n will have overhang, and we'll have center of mass. So when n equals 2, the overhang was 1, and the center of mass was 1/2. When n was 3, the overhang was 1.5, 3/2, 1 plus 1.5. It's not clear which one we like, and the overhang was 2/3. Is this enough data? Does anybody want to conjecture what the answer should be when n equals 4? Okay, so we have a conjecture that when n equals 4, the overhang should be 3/4. And what would you like to conjecture? I'm sorry, the center of mass should be 3/4. What do you want to conjecture? I'm sorry? Nope, these ones are actually good. But here's the box. So, what would you conjecture the overhang would be when n equals 4? Yes?
1 plus 2/3.
1 plus 2/3? Okay. Why 1 plus 2/3?
Because 3 is the overhang at 2 plus the center of mass at 2.
Okay. Other conjectures? 2. Other conjectures?
1 3/4.
1 3/4. Why 1 3/4?
Because every time you're adding double, you're increasing the overhang by about half.
All right. Any other conjectures? All right. So let's do some more analysis. Right. We at least have a couple of conjectures that are reasonable, but we don't really have enough data yet, and so we really want more data. So we now want to look at 4 dominoes. All right, so we have 4 dominoes. So we know the center of mass with 3. We know the overhang with 3. And now we need to just figure out where we want to put it. So here's the bottom. Here's 0. Here's -1. Here's 1. We know the center of mass is 2/3. So if we look at the next domino, we move 2/3 back to get to its center. And then we move 1 more back to get to its left end. So we have to start this one at -2/3. Because we move back 2/3, we're at 1/3. We then subtract 1, and we get to -2/3. So that's where the second domino goes. And it goes all the way to 1 1/3. Now the next domino, that's where we place this one, right? Now, where do we place this one on this one? We move over a half. And then the next one, we start that over the center of the next one. All right, let's calculate the overhang. How much is the overhang here? 1/3. Now we might see a good way of thinking what the overhang is. What was the overhang here? The overhang from the very first domino was 1. What was the overhang of the second domino? 1/2. What's the overhang we get for the next domino? Well, okay, the next domino is the one we just placed over here, which we just said earlier. It is 1/3. So is the pattern now becoming clear? What would you now conjecture?
1 plus 1/2 plus 1/3.
Right, and then if we had n plus 1 dominoes, we'd go all the way up to 1 over n. So our conjecture, I think, should be that if we have n dominoes, well, let's do n plus 1 dominoes. It's 1 plus 1/2 plus 1 over n. And then here, 1/2, 2/3, 3/4. It looks like the bottom is one less than, no, sorry, the bottom is one more than the top. So it should be n plus 1 over n as our conjecture. So let's check and see what is the center of mass with 4 dominoes.
Can I take those 4 dominoes for the card?
Oh,
Or do you still need them?
I don't know. I might need them, so it's worth keeping them. So let's calculate the center of mass. We have these 3 things here. And we know those 3 things here had a center of mass that was what? It was 2/3 past the center of the bottom. Right? So for these ones, we have a mass of size 3, and its location is 2/3 past the center of the bottom. Where is its center located? Its center is located at 1/3. Right? So I think it's going to be 2/3 past 1/3, so it should be times 1. Plus we have one mass at 0 divided by 4, and so we do get 3/4 as the center of mass. So our conjecture is beginning to look good. We now have some data point, and we can even see where these fractions, 1/2, 1/3, 1/4 are coming from, as we slide things further and further over. In the limit, what's the center of mass converging to? I think this is why I wanted to keep a few dominoes. So what's the center of mass converging to? What's its location converging to as we put more and more dominoes? 1. Would you be shocked if the center of mass converged to something greater than 1? Yeah, then the center of mass would be beyond the first domino and it would fall over. So it's a reasonable answer. It shouldn't be beyond 1. That's good. But the fascinating thing is that it's growing. We're getting the harmonic series. We'll see later that the harmonic series grows. If you sum up to n, it's like log of x. Log of n. So this goes off to infinity. Slowly. Okay? The log of 10 is about 2.3. Okay? The log of 10 to the 10 would be 10 log 10, which would be about 23. The log of 10 to the 100 would be about 230. 10 to the 100 is more than the number of subatomic particles in the universe. So if each little particle was a domino that we could use, we would not even move 1,000 domino lengths. This diverges, but diverges slowly. What my professor did is he found something that grew at either square root of n or cube root of n, phenomenally better. So what I want to do now is I want to talk about how you would prove these results. We're not going to prove them, but I want to use this as a way to motivate learning proofs by induction. So how many of you have seen proofs by induction? And Kim, you can actually raise your hand now because you did see it earlier today. All right, so how many of you have not seen proofs by induction? Okay, so again, we are now coming towards the end of the semester. I want to start giving you some of the tools and techniques that you can use in future math classes. I am not going to give you advanced, difficult problems like this on the exams, but I want you to be aware of the techniques, familiar with the techniques, and then when you see them in a future class, it won't be as bad. I will also prove, using induction, that everybody in the world has the same name. I will need a volunteer who has to have a government-approved identification on them. Is there a volunteer? All right, I saw your hand first. Do you have an ID? Okay. We will check and make sure. I will need to see the ID.
You said you're going to prove that.
I'm going to prove everybody has the same name.
No, you should do it.
Okay.
Should I get your approval there?
Yep, you get to prove it. Do you agree? You agree?
Yeah.
Okay. Okay. Oh, wait. Peter, just 1 second. Peter had a question.
No, I'm saying you should do it.
See, I said Peter had a question and you talked. Thank you. So you did prove that everybody.
You pointed at me.
You talked. You didn't say, Professor, my name's not Peter. You should know my name by now. You had your chance, Peter. You blew it. All right. Yes, Peter? I'm sorry, I thought Peter said something. All right. So we're going to talk about proving by induction. So the way induction works is you have some statement. You have a statement Pn. And the base case is you show P0 is true. Okay? Now, some people might start not at 0, they might start at 1, that's fine. Then the inductive step, you assume Pn is true, and then you prove Pn plus 1 is true. Then Pn is always true. If you start at 1 instead of 0, then what you would have is Pn is true for all n from 1 onward. If you start from 5, you would have Pn is true for all n at least 5. And here's roughly how it works. So you know P0 is true, and you know Pn, if Pn is true, then Pn plus 1 is true. We proved that statement. Let's take n equals 0. Then we know P0 true implies P1 is true. So P0 implies P1. So if P0 is true, and P0 implies P1, what do you know about P1? P1 must be true. Now we go back here. What should we take for n now? Yes? We shouldn't take it to be P1. What should we take for n? You're close, but not P1. Just 1. Now we take n to be 1, and we know whenever P1 is true, P2 is true. So we know P1 implies P2, so what can we now conclude? Now we know P2 is true. And you just keep marching down like this. So they sometimes draw this like a staircase. You know, here's P1, here's P2, here's P3, and you're just marching along. Okay? So I'm going to start off by proving the sum of the first n integers. So we've seen this before. We saw Gauss's trick where you write the numbers backwards and add and divide by 2. Here's a proof by induction. So let's Pn be the statement 0 plus 1 plus n is n plus 1 over 2. Okay? So the base case is P0 true? Does 0 equal 0 times 1 over 2? Yes, 0 does equal 0 times 1 over 2. So the base case is correct. So now we do the inductive step. So we assume Pn, and now we must show Pn plus 1. All right, so we're going to study 0 plus 1 plus n plus n plus 1.
Yeah.
Yes?
You always tell me not to assume.
Does anyone know what happens if you assume? You make an ass out of you and me. All right. So we are trying to understand this sum. How many of you have never seen that one? All right, there's a great odd couple skit on this. I will try to remember to include that in the comments from today's lecture, where they do that in course. And if they had just stopped there, they would have won the court case. We want to understand this sum. We're assuming that Pn is true. Pn is the sum of the first of the integers up to n. So by assumption, we know what this is. What would that equal?
N times n plus 1 over 2.
Good, so it's n times n plus 1 over 2, and then we have to add to that n plus 1. How do you add two fractions? Common denominators. So we multiply by 2 over 2, and we'll get n plus 1, n plus 2 over 2, and we can write that as n plus 1, n plus 1 plus 1 over 2. And that's Pn plus 1. So we've now shown Pn plus 1 is true. This is a lot easier because I told you what the sum equals. If I don't tell you what the sum is, it's much harder. There are ways to figure out what that sum should be, but it's a little bit harder. All right, let's do one more. Let's let Pn be 0 squared plus 1 squared plus n squared is n plus 1, 2n plus 1 over 6. So the first is the base case, P0. So does 0 squared equal 0 times 1 times 1 over 6? Yes. So now let's do the inductive step. So we assume Pn, and we must show Pn plus 1. All right, so we're assuming Pn is true. So we're looking at 0 squared plus 1 squared plus n squared plus n plus 1 squared. But by assumption, we know what the sum of the squares up to n is. That's going to just be n plus 1, 2n plus 1 over 6. And now we multiply by n plus 1 squared. I'm going to write that as n plus 1 times n plus 1 times 6 over 6. And in section 1, I made an algebra mistake. I forgot the 6 in the numerator when I factored things. So I can now write this as they both have an n plus 1. I'm going to have a 2n squared plus n from these two terms. Then I have a plus 6n plus 6 divided by 6. So this is just now algebra collection. So at this point, we just have to do the algebra correctly. And now when you simplify, this is just n plus 1, 2n plus, n plus 1, n plus 2, 2n plus 3 over 6. And if you square, you get 2n squared plus 4n plus 3n is plus 7n plus 6. And that's exactly what it should be. There's also a formula for sum of cubes. There's a formula for sum of fourth powers. It turns out that it's always going to be a polynomial. The leading term here is 6. So we have a little bit of time that we didn't have in section 1, so I'll just give you a quick idea. And this is another precursor to the integral test. So let's look at 0 to the p plus 1 to the p plus 2 to the p plus 3 to the p all the way up to n to the p. So this is going to be the sum, m goes from 0 to m to n of m to the p. Okay? Do you agree that that's kind of like integrating from 0 to n of x to the p dx? And then that should be x to the p plus 1 over p plus 1 at 0 and n, which is n to the p plus 1 over p plus 1. So if we want to just get some rough sense of the size, it looks like it should be n to 1 higher power divided by p by that 1 more than that power. And if you look at what we have, here we have n, so we'll have to go over here. So we have n plus 1, 2n plus 1 over 6. That's a 2n cubed over 6. That's an n cubed over 3. That's exactly what seems to be indicated here. So, again, this is not a proof, but it does give you a suspicion that it should look like n to p to the 1 more divided by p plus 1. The fact that it's a polynomial is amazing, but because it's a polynomial, if you just choose, it's a polynomial of degree p plus 1. If you just choose enough points, you can actually find out what the polynomial is, and then you can feed that into the induction. What do you think the constant term of the polynomial has to be? So the main term is, 1 over p plus 1 is the coefficient. If we just sum 0, what do we get? 0. So when n equals 0, you have to get 0. What does the constant term have to be? Because if you take n equals 0, you have to get 0. So what must the constant term be?
0.
It has to be 0. So you actually have an idea of what the first and the last terms are. And that saves you enormously. All right. So I'm now going to prove that everybody is named Peter. Proof everyone is named Peter. All right. So Pn is the statement in a group of n people all have the same name. Okay? So in any group of n people, I'm going to assume everybody has the same name. Let's do the base case. Is P0 true? If I have a group with no one, does everybody in the group have the same name? Yeah, but you might be a little bit uneasy about this because there's nobody in the group. So let's do P1 as well. If I have a group with just one person in it, does everybody in the group have the same name?
Yeah.
Thank you, Peter. Okay, so now let's do the inductive step. So we assume Pn. We must prove Pn plus 1 is true. All right. Did you want to draw people, Cam?
We should get one of the guys with Mohawk.
I'm sorry?
We should get one of the guys with Mohawk.
The Mohawk? All right.
And faces. You should definitely
And this
get
person's
people
been
faces.
drinking a lot. All right. 1, 2, 3, 4, n minus 1, n plus 1. I am sorry to say Peter does have a drinking problem. Okay. So if we look at this, we know whenever we have a group of n people, they all have the same name. Can somebody give me a group of n people? You're not eligible, Cam. I'm sorry? Well, of these n plus 1 people, I need a group of n people from these n plus 1. I'm sorry? What? No, I'm saying I want to choose n people from these n plus 1. Give me a way of choosing n people from n plus 1. Tell me which n people I should choose. The first n. That's an easy one. Give me another choice. You've already done section 1.
What if I wasn't listening?
Then you'd be in trouble for not listening. Yes.
From 2 to n.
Yeah, I can do the second. So everybody in the first group of n has the same name by the inductive assumption. We're assuming whenever we have n people, they all have the same name. the last group of n people all have the same name by the inductive assumption. But person 2 is in both groups. Person 3 is in both groups. Person 4 is in. Everybody has the same name. So everybody in the first group has the same name as person 2. Everybody in the second group has the same name as person 2. So everybody has the same name as person 2. We've now shown everybody has the same name. And since I know that one person in the world is named Peter, I now know that everybody in the world is named Peter. What is wrong with this? Yes, Peter. Or potential Peter, potential Peter, potential Peter.
You assume that everyone had the same name.
I'm only assuming that everybody in a group of n has the same name. That's the inductive assumption. I'm allowed to assume that the statement Pn is true, and then I show Pn plus 1 false. I showed P1 is true. Now you go. Yes, Peter. Or potential Peter.
That's just not how the world works. It's like in
Prove it to me mathematically. This is not a humanities class. This is not a poli-sci class. This is a math class. I need a math proof.
You're assuming that n could be any number. And
Yes.
It could still be true, but that's not like if you analyze it with data, it doesn't really.
I'm a pure mathematician. I don't understand this word data. This is a proof. What is wrong with the proof? Yes.
If you test a base case that's greater than 1, could you, like if you test like base case of P2?
Okay, now you're getting very close. You're very close, yes.
You're saying the first n people
Mm-hmm.
have the same name. You can't change the grouping of n
My
people.
statement is not, my statement is any group of n people have the same name. I'm not assuming two different groups of n people have the same name. I'm saying whenever n people are together, they all have the same name. All right, what do you want to say, Cam?
I guess I can't say.
You can say it. It's close to what was said.
If you have 2 people,
Mm-hmm.
first person would be his elder, but the other guy would be their group, and they would be different groups.
So if n equals 1 and n plus 1 is 2, the groups are disjoint. There is no common person. The case P1 implies P2 is false. This proof shows you that Pn implies Pn plus 1 if n is at least 2. I subtly assumed something. By drawing it like this, well, usually the small cases are not a problem. It's only the very large cases in the end that become difficult. So this does not prove that everybody in the world is not named Peter. It just says that this is not a correct proof that everybody's named Peter. So anybody who's not named Peter and has ID, now you can restore your name. Okay? But it's very easy to make these little mistakes. If you think about it, imagine that whenever you have a group of 2 people, everybody has the same name. Well, then if I have 100 people, I group 1 and 2 together, they have the same name. Then I group 2 and 3 together, and 3 has the same name as 2, has the same name as 1. Then I group 4 and 3, and I march down like that. This is similar to how we prove some rules of differentiation with groupings and parentheses. The big case to do was the n equals 2. Once we had n equals 2, we could get everything else. So once we have 2, we have everything else. We don't have 2. You can prove a lot of strange things by induction. You can modify this proof to prove that every integer is a perfect square. There's a lot of fun things you can do. Okay, this is a good place to end. So we saw a lot of stuff today. We saw the harmonic series arise naturally. We saw how to gather data, and I know I was a little bit hard on data a moment ago. I love data. We gathered some data. We made some conjectures. And now, as good problems, try to prove the center of mass and the overhang. You want to do them together.